Okay, so here we are in section 5.9, complex numbers. I think this is the last section of this particular chapter, and so our assignment is going to be on page 274, numbers 19 through 63, odd and 64. Let's chit-chat a little bit. Complex numbers make up the realm of all numbers. So technically, here's like the family tree of numbers. I'm going to say all numbers can be written in this form, a plus bi, where I is something we're going to learn about today. It's an imaginary number. And so basically, we have two branches of numbers. We've got the reals and we've got the imaginaries. All right. And so imaginary numbers are something that we've never talked about before, and that's what this I business is about. Real numbers we know break down into two categories. We've got rational, which are numbers that we can write as fractions, and then we've got irrationals, which predominantly look like, for us anyway, radicals. So anything we can write as a fraction is rational. Anything we can't write as a fraction or as a ratio of two integers would be irrational. Square root of 3, pi, all that stuff. Imaginary numbers have this thing where it always has an I in it. And that's what we're going to talk about today. That's what's important for us today. So we've got two types of imaginary numbers. Well, really, we've got imaginary numbers, and then we have something called pure imaginary numbers. All right. So pure imaginary numbers is something also that we'll talk about today as well. And so we'll look back at this at a later time and kind of bring our thoughts together from our lesson today. So our vocabulary today starts off with the concept of an imaginary unit, and an imaginary unit is this idea of the square root of -1, which we were told you can't do. You can't take the square root of a negative number, but mathematicians have allowed for this concept of, well, let's give this a value. So the square root of the square root of -1 is considered I. It is an imaginary number. It's not real. It doesn't have a whole lot of real life applications, but it does help with calculations that apply to real life situations. All right. So that's something that you probably won't see until higher level math, but I want you to know that the definition of the square root of -1 is I. That's the definition. And then if I talk about I squared as a number, it is the square root of -1 times the square root of -1, which is -1. This is the definition, and I'm pointing this out so that we know that this is kind of an anchor that we need to hold on to. This is nothing that we calculate. All right, and we'll talk about how that works out a little bit later. Pure imaginary numbers, and we kind of alluded to that earlier on. Pure imaginary numbers are numbers for us that just have an I in it. So if I had like 3i, that's a pure imaginary number. -2/4 I, or maybe 2/3 would have been better because that's reducible, is just a pure imaginary number. It's a regular number times I. A number that we're used to times I is a pure imaginary number. When we get to the context of complex numbers are any number that I can write in a form that I like to call a plus bi, meaning if I can write a regular number plus some I form of a number, I have a complex number. So for instance, 3 plus 2i is a complex number. -7/5 minus 3/4 I is a complex number. But here's the thing. This is why I said all numbers are complex numbers. I can write the number 7 plus 0i like that. Well, I have no i's. Basically, that's just the number 7. I can consider that a complex number. So all numbers technically can be written in complex form. And if I'm dealing with the real numbers, the b value is just 0. The a plus bi, the b value is 0. When I'm dealing with imaginary numbers, the b value cannot be 0, meaning I got to have some imaginary part to it in order to call it imaginary. In order for it to be real, the imaginary part has to be dead in a sense, so I've got to put a 0 there. So all numbers are complex, and I can write any number in this complex form where I've got some number a plus bi, a plus a complex value. All right, and so absolute value is going to be, the absolute value is going to require for us to kind of dig a little bit deeper. So I want you to zoom in with me just to think about this. So to consider the absolute value of an imaginary number, we have to actually think about first graphing it. So when I graph an imaginary number, I basically graph it on something that looks like the x and y axis, but what we actually have is a real axis and an imaginary axis. So I take this number and I graph it, the real part on the what we used to call the x-axis, and the imaginary part on the y-axis, and that's going to be up 3i. So this would be I, 2i, 3i, and here this is 1, 2, and 3, and so forth and so on, and I'd have negative numbers here and negative I values here. Since this is positive 2 plus 3i, the value is here, so I've graphed it. So how do I figure out what the absolute value is? The absolute value is going to be the distance from this number graphed to the origin, right? The origin being that 0, in this case 0, 0i point, right? 0, 0 point that we're used to. And to find that out, we're going to actually have to do something that I don't know if you remember or if you ever learned it. It's called the Pythagorean theorem. And it basically tells me how to find the distances around a right triangle. So in a sense, when I draw this line, this is the hypotenuse, the longest side of a right triangle. And the Pythagorean theorem says if I have a squared plus b squared equals c squared, okay, that would be the relationship between the lengths of the sides of a right triangle, where C is always the longest side, the hypotenuse. So if I were to find this length here, this length in red, the relationship between all of these sides would be as follows, right? The a squared plus b squared equals c squared thing. So the length of this side is 2, so 2 squared, the length of this side is 3 plus 3 squared equals c squared. That's what I'm trying to tell you. I know this is a bit involved, but it's in your text and I think it's worth knowing. 2 squared is 4, so we get 4 plus 9, right? 4 plus 9 is equal to our c squared. Still trying to find that red length. And then 4 plus 9 is going to give me 13. So I have 13 is equal to c squared. How do I undo something that's being squared? I take the square root of it. So both sides I take the square root of, and I get c is equal to the square root of 13. Let me write that in red so we know what we're talking about. And so when I talk about the absolute value of a complex number, in this case, I would get the distance from the origin to that number on this imaginary plane is going to be the square root 13. All right, let's get out of this. I know that was a whole lot. This is going to be a longer video than usual, and that's all right. So that was our absolute value definition, and the final definition that we're going to talk about is complex conjugate, and this isn't too bad. Complex conjugate is just like the other conjugates we've talked about before. Since we're familiar with conjugates already, we know that, you remember back in the day, 3 plus the square root of 2 has its conjugate. Its conjugate is 3 minus the square root of 2. Complex conjugates work exactly the same way. If I have 4 plus 2i, then its conjugate would be 4 minus 2i. If I had 7 minus 3 halves I, then its conjugate would be 7 plus 3 halves I. So we're going to use all of these concepts, or at least most of them, in the examples that we'll talk about today. Let's take a look at the square root of negative numbers. So when I take the square root of negative numbers, what I need to do is, and this is going to sound silly, but I tell students all the time, pop out the I. Okay, so the fact is I can look at this as the square root of negative 1 times the square root of 18. Well, I already know what the square root of negative 1 is. It is defined as I. So I write this as I times the square root of 18. You know how to simplify the square root of 18. We look for a perfect square, or we can prime factorize it, right? So I have I times 3 squared times 2, because that's 9 times 2 is 18. 3 squared is going to give me 3 when I take the square root of it. So I notice where I'm putting the 3. I put the 3 on the left side of I, and I leave the radical on the right side of I. So I have 3i square root of 2, and that's my final answer. Okay, so that's how I go from here to here. Let's look at this one over here. Remember, the first thing we do is pop out the I. So I'm going to pop out the I by honoring the fact that there's a negative I in there, and I've got a negative 1 rather, and I've got 125 x to the 5th power. I like to deal with the I first. When I pop it out, then I've got a regular problem that I'm used to. So I'm used to 125 times x to the 5th power, taking the square root of that. I'm going to just rewrite this. Let's prime factorize it, just because I did that last time. It felt kind of good. So this is 5 times 5, that's 25, times another 5. So this is 5 to the 3rd power. Here, this is x to the 5th power. Let me write it like this. I can look at 5 to the 3rd power as 5 squared times 5, and I could look at x to the 5th power as x squared times another x squared times x. And so if I take the square root of each of these guys, I end up with I times 5. And then this 5 stays underneath the radical. I get 2 x's out, so that's x squared. And then what stays underneath the radical is the 5 and the x. So I end up with 5i x squared times the square root of 5x. And that's all I can do for this problem. Let's try example 2. Here in example 2, we are multiplying I. Now, if you remember when we discussed this before, we know that I to the 2nd power is equal to, it's defined as -1. So let's keep that in mind when we're trying these problems out. So what I have here is -2i times 7i. -2 times 7, we know to be -14. I squared, we just defined it as -1. So I could actually write this as -14 times -1, which we know to be +14. And that's the end of that problem. If we take a look at this next one, remember what we mentioned before. When you have this kind of a radical, the first thing you want to do is pop out the I. So if I have a negative square root of 10, I'm actually going to look at this as I times the square root of 10. Remember, that -1 is going to be that I. Over here, we have the same situation. The square root of 15, -15, is going to be I root 15. Now what I can do is multiply the things that are on the outside of my radical together, and I can multiply the things that are inside the radical together as well to see if something good happens, if I could simplify further. I times I, again, is defined as I squared, or -1. So when I bring these two guys together, I get a -1. Square root of 10 times the square root of 15, since they're both under the same radical, I'm going to write them together as 150. The question you should be asking yourself now is, can I simplify the square root of 150? And the answer is yes. Prime factorize that or divide out by a perfect square. I'm going to choose to divide out by a perfect square at this time. So I know that 25 goes into 150 6 times. So I'm going to write this as the square root of 25 times 6. Square root of 25 we know to be 5. Square root of 6 we can't do, so it stays there. And recognize that this is actually a -5 times the square root of 6. And now we're done. This will probably be the last problem for this part of the video, just because it's going to be a little bit long to explain. We have several other examples, so definitely look for the second part. But take a look at this. We have a weird problem. It's I to the 45th power. What we know about I so far is that I is equal to the square root of 1, -1 rather, and I squared is equal to -1. How can we use that information to actually simplify this situation? What we're going to do is actually look for a pattern. And the way we do it, oftentimes mathematicians have to do this, you have to look to see what's happening before you get to a particular value to predict or actually make an educated guess about what's going to happen at that value. So let's say I had I squared. Well, if I have I to the 1st power, we know what that is. It's just I, or the square root of -1. So let's write that down. If I have I squared, we're given the definition that I squared is -1. So I'll write that. What about I to the 3rd power? Recognize that I to the 3rd power from our rules of exponents can be written as I squared times I. If that's the case, I squared is -1. I can write that as -1 times I. -1 times I is just going to be -I. Let's hold on to that thought. Let's look at I to the 4th power. If we look at I to the 4th power, we end up with I squared times I squared, right? Rules of exponents, I to the 2nd power times I to the 2nd power is simply I to the 4th power. Remember what I squared is? It's -1. So I have -1 times -1. And when I multiply those guys together, I end up with a +1. Let's review what we just did. I to the first power